All right, let's do this. Okay, so last week was all focused around molecular structures, right? And so we ended the week with talking about those different geometries. And then for your homework, you built these molecules in that program and spun them around to try to get a sense of what these geometries are, right? So to be clear, the name of the game is like, if I say tetrahedral, you want to have something come to mind about what shape I'm talking about, right? That's what kind of familiarity that we want. On our exam, you'll be given a word bank of all these different geometries, right? So I'll tell you what all the names are, but you need to know what those geometries are. That's the name of the game, okay? Now, we don't have that little fancy computer program to draw these things out on an exam, okay? So instead, how do we represent the 3D structures of a molecule? We're going to use what's called the perspective drawings. All right, so that's what we're going to learn how to do today, are these perspective drawings. All right. These are a way to convey the 3D geometry of a molecule in a 2D drawing. All right. Importantly, your Lewis structures do not tell you the geometry of that molecule, or at least they don't look like the geometry of that molecule. We can kind of interpret the information in a Lewis structure to get to the geometry. That's what we were working on last week. But what we write down on the paper isn't the shape of that molecule. It just tells us who's bonded to who and where the electrons live. All right. So these are going to be drawings that do convey that shape. And we're going to have a few different types of bonds that we're going to use here. All right, the first are the ones that we already know, our straight line bonds. All right, within our perspective drawings, these are going to represent bonds that are parallel to the plane of the page, which is a fancy way of saying that they're flat. All right, they're just sitting flat in that two-dimensional structure. Okay, and there are two geometries. We're going to take a look at the electron geometries first, all those different electron geometries, and then we'll kind of move from there. And there are two electron geometries that we can represent with only these straight line bonds. All right, the first, what did we call this one? Linear. So here's our fancy computer program of our linear structure. If we wanted to do our perspective drawing, all right, notice that both of these bonds, the way that I've sort of oriented this molecule, both of these bonds are sitting flat on that page. Nothing's pointed out at you or into the board. They're just flat here. So we can represent these with just those straight line bonds in our perspective structure. All right? So our perspective structure of a molecule that's linear is going to only have those flat straight line bonds. Okay, just two line segments, one right after the other one. All right, we can also do this geometry right here, which is what? Which would this one be? Trigonal planar. And again, because all of these bonds are, this is a planar molecule, all these bonds are flat on the page right here. So my perspective drawing, I would just draw all three bonds using that straight line bond. All right, so again, our perspective drawing of a molecule that's trigonal planar is just going to have these three straight line bonds. Okay? Cool. So as soon as we get to geometries that are more complicated, all of a sudden this isn't going to work. Like if we take a example, this one here, what would this one be? With these 4 electron regions, that is that tetrahedral geometry. And if we look, 2 of these bonds are indeed flat. They're parallel to the plane of the page, but 2 of them are not flat. One of them is sticking out at us, and the other one is pointed back into the page here, all right? So we need to learn 2 new types of bonds that we're going to be able to draw. We set our straight line bonds. These are the flat ones, the ones that are parallel to the plane of the page. We're going to use these wedge bonds, all right, which we just call wedges. These are used to represent bonds that are pointed out of the page, so pointed towards you all, right? A bond that's sticking out of the page this way. So again, by that I mean pointed towards you. Okay, and if the bond is pointed in the other direction, we use these dash bonds, kind of that same triangle shape, but we make them out of dashes. All right, and unlike the wedge means it's pointed out at you. The other one means that it's pointed away from you, so pointed into the page. All right, away from you. All right, so we need to go to our tetrahedral structure and turn this into one of these perspective drawings. All right, so let's just kind of zoom in here on our image. If I label these A, B, C, and D, which 2 can we represent with just that straight line bonds, just our regular old line segments? B and C, right? So these 2 here are in the plane of the page. I'm just going to represent those 2 with my straight line bond. All right, but what about D? What type of bond should I be using for that one? A wedge, because this bond is now pointed out towards me. So I'm going to use a little wedge shape here. All right, and then what about A? A is pointed into the board. So I'm going to use one of those dashed bonds for A. All right, so just to kind of copy this over here, this is our perspective drawing for that tetrahedral geometry. These dashed and wedged bonds are a very common way to show molecular geometry. When you go on to organic chemistry, you'll see these things all over the place. All right, so this is our tetrahedral here in this perspective drawing. Okay, we got 2 more, because again, we're going through all of our different electron geometries. All right, we have our trigonal bipyramidal. And then the one with 6 electron regions, what do we call that one? Octahedral. All right, so I'll kind of zoom in on these here as much as I can, but I want you to see if you can figure out how to do the perspective drawings for these two molecules right here. Using those straight-lined, dashed, and wedged bonds, how are you going to show these two geometries? Okay, so let's do this one first. How many of those straight line bonds should I have in this drawing? 3. So this one here's 1, this one over here's 1, and this one down here is a 3rd. Then I got this bond right here that is pointed out towards me, so I'm going to use what type of bond for that? A wedge. All right, the other one is pointed into the page, so for that one I'm going to use my dash. All right, so my perspective drawing of this trigonal bipyramidal structure, again, has those 3 straight line bonds, 1 wedge sticking out, and then 1 dash sticking behind. Okay, an octahedral here. Now we should have 4 straight line bonds. 1, 2, 3, 4. We got this one pointed out of the page, so this one we're going to put on a wedged bond. The other one pointing into the page, we'll put on a dashed bond. Cool. So the goal here being to read these perspective drawings here to be able to tell what geometry they are conveying. Right? Again, keeping in mind that these wedge bonds are a bond that's sticking out of the page, and these dashed bonds that are pointed back into the page. All right. The next thing we're going to talk about here, we're going to go through and label all of these with what are called their bond angles. Okay, and our bond angle, this is just the angle between 2 covalent bonds. Cool. All right, so our linear structure, this is going to be the easiest one here. what is this bond angle here between these two bonds if they're on opposite sides of that central atom? 180 degrees. And we've been talking about temperature for a while, not 180 degrees Celsius, just 180 degrees. Okay, if we go to our trigonal planar here, this one's a little bit harder, but I think we can ration through this here. All right, if I went all the way around, how many degrees would that be? 360, and this was broken into 1, 2, 3 equal parts here. So what's 360 divided by 3? 120. All right, so the bond angle here between all of these bonds is 120 degrees. All right. A tetrahedral, you can do some very complex math here and convince yourself of this, but let me just tell you, a tetrahedral has all these bonds equally spaced out, and there's this magic number that we just got to know for a tetrahedral bond angle, and that is 109.5 degrees. All right, we just got to know a tetrahedral is 109.5. All right, our trigonal bipyramidal. This one's kind of one of the tougher ones. Let's actually pull this up in our little fancy program here. Okay, we got a few different things going on here. So what about this bond angle on the left, nope, on the right, between these atoms here that I've colored in pink, this tiny little pink dot, I don't know if you can tell. So these are 90 degrees from one another, right? And what about if I pick these two that are on opposite sides? What are those? Those are 180, all right? But what about the ones around the middle? We got these 3 ones around the middle here. Remember, this is trigonal bipyramidal, so this is our triangle base of our pyramid. And much like our trigonal planar structure, all 3 of these lie in that same plane. So what will be the bond angle between these middle ones here? 120. All right, so we got a few different ones to worry about here for our trigonal planar. All right, nope, that's not what I meant. For our trigonal bipyramidal, we have these 90-degree angles here, as well as, if we're going to pick opposite sides, 180. All right, but then all of those middle ones are 120 degrees apart from one another. That's that triangle in our trigonal bipyramidal. All right, and then an octahedral. So again, we can see we got 2 of the same ones here. What do we see? Somebody shout them out. So we got 90 degrees. So all of these are either 90, or if I pick them on opposite sides, 180. Okay? And that goes for even these ones that are pointed into and away from the page. If we just kind of rotated this structure a little bit, we could see that those are also sitting 90 degrees to their neighbors, or 180 degrees from one another. Cool. All right, so now we sort of focused only on the perspective drawings of our electron geometries. All right, so how do we get perspective drawings of all of our other geometries? All right, so specifically when we have lone pairs, on that central atom. So let's just do 2 comparisons here next to one another. We're going to do CH4. This one we've done the Lewis structure for. That's carbon in the middle bound to these 4 hydrogens. And then we're going to do NH3, which is nitrogen. It's bound to these 3 hydrogens, but then it's got a lone pair on that central atom. All right? So what we're going to do is in all these cases, we're going to start with our electron geometry. Okay, so how many electron regions do we see in methane here in CH4? 1, 2, 3, 4, which means it's sp3 hybridized and has that tetrahedral geometry. And in this case, there are no lone pairs on that central atom, so what's its molecular geometry? Also tetrahedral. Cool, so take a minute and draw me the perspective drawing of that methane molecule. All right, so this is both the electron geometry and the molecular geometry of methane of CH4, that tetrahedral shape. All right, let's just label that. Okay, so if I want the molecular geometry of this molecule here, ammonia, NH3, I'm going to start with its electron geometry. I'm going to start with that tetrahedral. Okay? Now, let's remember, when I was showing you these shapes here, and we were talking about getting the molecular geometry, I said, oh, well, lone pairs, they're invisible. We can't see them, right? So what I'm going to do here is I'm going to go and I'm just going to say, all right, let's hide this bond right here. Now that's my invisible lone pair. And this gives me my molecular geometry of this ammonia, what we called trigonal pyramidal. If you remember, it's a little triangle, but it doesn't sit flat. It's kind of got this little squat pyramid shape to it, right? So this was our trigonal pyramidal. But what did I do is I took this model and I just deleted one of those bonds, right? Because that was that invisible lone pair. So what am I going to do with my perspective drawing here? I'm going to start with my electron geometry, my tetrahedral, and I'm going to get rid of one of those bonds. Boom. There is my molecular geometry of my ammonia, right? We have this invisible lone pair here, but again, we can't see that. We're talking about the molecular geometry. So this is our trigonal pyramidal. Okay. Now, to be clear, it wouldn't matter which one of those bonds. They are all equally spaced apart. It wouldn't matter which one you got rid of. But if you kind of leave it looking like this, it looks a little bit more, at least to me, like a triangle-based pyramid, which is what the name of that geometry is. I could turn this thing on its side, and it doesn't change the geometry. It would change the way that we drew it. Now we would draw it with 2 straight lines and 1 dashed line. Right? That would be as if I deleted this one over here. That's perfectly fine. It just doesn't look as much like a triangle-based pyramid anymore. So sometimes you can be strategic about which one of these bonds you erase, and it'll give you a figure that looks a little bit more like the name of the geometry. but in this case, it really wouldn't matter which two I picked. All right, so given that same logic, I want you to now give me this perspective drawing of water. All right, we had that central oxygen with 2 lone pairs bound to 2 hydrogens. Everybody take a second and give me the perspective drawing of this molecule here. All right, what are we going to start with? That tetrahedral perspective drawing, because again, this is my electron geometry of water with its 4 electron regions. And I'm going to go through and I'm going to scratch how many of these bonds? 2. So again, it doesn't matter which 2 you pick. That one and that one. There's my perspective drawing of water. I could have picked this one and this one. I could have picked this one and this one, right? It doesn't matter. I just need to get rid of 2 of them, and that will leave me with my, what do we call that? Bent geometry. All right, so just to kind of look at these next to each other, this is kind of the important thing. This is really our goal of lab today. In your lab activity, you're going to be building these molecules with these model kits and then drawing their perspective drawings to kind of get a sense of how these little dashed and wedged bonds work, right? Again, you want to sort of be able to look at this thing here and see that it is in the shape of a pyramid because one of those bonds is sticking out at you and the other one is pointed into the page. All right, so we're starting with our electron geometry. We're going to erase bonds to replace them with their invisible lone pairs. All right, cool. So for these ones, I told you it wouldn't matter which bond you picked. When we get to our expanded octet structures, that's not really the case anymore. So we're going to do another 2 examples here. PCl5 and SF4. And for the sake of time, I'm going to remind you these are Lewis structures that we did before. So you could check in your notes or just check up here. Okay, but then more importantly, I want you to take these and take this first one at least and convert it into its perspective drawing of that molecular geometry. All right, so this one have PCl5 has how many electron regions? 5. So what was the electron geometry with 5 electron regions? We made a master cheat sheet. We should be able to look this up in our notes here. 5 electron regions is what electron geometry? Trigonal bipyramidal. And that was that shape that we did before. We have a little T, we have one bond sticking out at us, and another one pointing into the page here. Okay, and since phosphorus pentachloride doesn't have any lone pairs on that central phosphorus, its molecular geometry is also trigonal bipyramidal. Okay, so if I were to do my next structure, the sulfur tetrafluoride, now I have those same 5 electron regions. So I'm again going to start with that same electron geometry perspective drawing. But now there's that lone pair on my central atom. So what do I got to do to this structure here? I got to go through and erase one. All right. But unlike our tetrahedral, here we have 2 very different bonds. We have some bonds, these ones here, that are 90 and 180 from one another. But then we have the 3 in the middle that are 120 degrees from one another, right? So this isn't this perfectly symmetrical structure like we had last time, where it wouldn't matter which one we chose, okay? So in order to figure out what we got to get rid of, there's one sort of operating procedure that we're going to go through here that we're going to use, okay? And that is the fact that lone pairs occupy more space than bonding pairs. Lone pair electrons. Occupy more space than bonding pair electrons. All right, so we need to delete the bond that gives that lone pair the most room. All right, so let's see if we can't reason what that would be here just looking at our perspective drawing. Okay. Oops. Okay, so I'm going to either choose one of these ones that are on the opposite ends of one another, so like this one here, or one of the 3 that make the triangle in the middle, like this one here. And I want to figure out which one, if I get rid of it, would give me the most room for that lone pair. All right, so let's think about that. Let's get rid of this blue one here. We'll sort of imagine we have our lone pair. This lone pair is now sitting 90 degrees to these 1, 2, 3 bonds here. All right, all 3 of those ones in the middle. If I get rid of the red one, this lone pair is sitting 90 degrees from 1, 2 other bonds. All right, and it's got these other bonds, but they're much further away. So which one of these is going to give the lone pair the most room? The red or the blue? The red position here, okay? So this one here, and let's see if we can see, is our molecular geometry. Maybe if we flipped it on its side and started rocking it back and forth, that would remind us that this one had what ridiculous name? Seesaw. So this is our seesaw geometry here. All right, so importantly now, we have to be strategic about what bonds we're deleting. We want to make sure to delete this one right here delete to give lone pair max space. And this is our seesaw geometry. All right. There's actually another consequence to this lone pairs occupy more space than bonding pairs rule here, and that has to do with our bond angles. So let's take these three examples here and go through and assign bond angles here. All right, our tetrahedral bond angle. This was the number we just got to know, right? We just got to remember this one here. What is that? 109.5 degrees. Turns out that if you want to space four things out evenly, you put them 109.5 degrees from one another. Okay? So now if we go to our trigonal pyramidal, this starts again as that tetrahedral geometry, right? So if I imagine my lone pair here, it's pointed up just where that bond that we deleted was, right? So it's got all those pairs of electrons have that tetrahedral geometry. But again, this isn't this nice, skinny bonding pair of electrons. It's this big, fat lone pair of electrons. And that lone pair occupies a bunch of space, so much that it actually pushes all the other bonds a little bit closer together. So it turns out that these bond angles are closer to like 106 as opposed to 109.5. We're not going to try to remember exact numbers or anything like that. What we're going to say is when there's a lone pair on that central atom, that means that our bond angle is now less than 109.5. Not a ton less, but it is less than 109.5. All right, so we're going to use that less than symbol and say these bond angles now, because of those lone pairs, are slightly less than what they would be ideally, that 109.5 number. All right, same thing for water. Water's got two lone pairs on it, right? Its true bond angle is closer to like 105, but we're not going to try to remember exact numbers. We're just going to say less than that tetrahedral bond angle of 109.5. So lone pairs, push bonds closer, so their bond angle is less than ideal. Actually, let's say lone pairs on central atoms specifically. Cool. All right, so this is sort of a great example of all the things that we can do now from our discussion of structures. I can give you a formula like CH4, and you can tell me what its Lewis structure is. You can then take that Lewis structure and count the electron regions and tell me what its electron geometry and its molecular geometry is. And you should know the names of those different geometries. And from there, you can tell me what the bond angle is as well. And there's one more thing that you need to be able to tell me of these structures, and that is whether they are polar or non-polar. All right, and we did talk about this a little bit with respect to our chapter on solids and liquids. All right, but now that we have all these different Lewis structures, we need to be able to classify them as being polar or non-polar, okay? So first of all, we got to distinguish between molecular polarity And the first type of polarity that we introduced, which is simply bond polarity. Bond polarity means that there's an uneven distribution of electrons in a covalent bond. All right, so one that we kind of looked at a lot was like a carbon-oxygen double bond. This thing is a classic organic bond that you see a whole bunch. It's definitely a polar bond because oxygen's right next to fluorine. It's very electronegative, so it has this partial negative charge, and it's stealing all that charge from that carbon, so carbon has a partial positive charge. So here's an example of a polar bond. All right, how do we know that a bond is polar? I kind of already gave away the punchline here. It specifically has to be between atoms of differing electronegativity, right? One of them has to be better at pulling electron density onto itself than the other atom. So these are bonds that are between atoms of differing electronegativity. All right, but we need to distinguish this with molecular polarity. And it's got that same basic concept, again, an uneven distribution of electrons. But now this is across an entire molecule. All right, so an example would be a water molecule. Man, if there is one molecule you need to know is polar, it is water. All right, water consists of these polar bonds, right, where oxygen is more electronegative than hydrogen. So that oxygen is stealing electron density in this bond from this hydrogen, but also in this bond from this other hydrogen. All right, so that means that there's an unequal distribution of electrons across this entire molecule. You can see the way that I've oriented it here. This whole molecule has one end with a negative charge, with a partial negative charge rather. And on the other end, between those two partially positive hydrogens, it's got that partial positive charge. All right, so it's got these two polar bonds. That's an important part of our molecular polarity. But I can sort of turn this molecule in such a way so that all the negative charge is on one side and all the positive charge is on another side. All right, that's our molecular polarity. Okay, so now we're going to talk about our rules for being polar. All right, so when we look at a molecule, how are we supposed to be able to classify it as being polar or nonpolar? All right, rule number one, the most important rule, is it has to be made, it has to be composed of polar bonds. Right, so all molecules that have molecular polarity are made up with bonds that have bond polarity. All right? But then rule 2, they also have to have this asymmetric molecular geometry. All right? So, what do I mean by that? Let me kind of explain this by doing a counter example here. Okay, carbon dioxide has that linear geometry. And is carbon dioxide composed of polar bonds? Yeah, we talked about how these bonds, if I look at each one of these bonds individually, I'd say, oh, oxygen is more electronegative, so it's got this partial negative charge. And carbon's less electronegative, so it has a partial positive charge. And then I would say the exact same thing on this side. All right? So although this is composed of these polar bonds, one negative end's pointed this way, and the other one is pointed in the exact opposite way. There's no way that I can orient this molecule such that 1/2 is positive and 1/2 is negative. That negative charge is evenly distributed around that central atom. So because this here is a symmetric structure, it's nonpolar. There is no uneven distribution of electrons from one side of the molecule to another. All right, so again, another quality here of our polar molecules is that they have to be asymmetric. So how the heck am I supposed to be able to spy that? Like, what do I know is symmetric or asymmetric? Okay, so there's 2 easy ways to spy an asymmetric structure. All right, first of all, not all bonds are identical. So if, for example, instead of being carbon dioxide on one side was a bunch of hydrogens, now all of a sudden that would be a polar molecule. It would lose its symmetry, right? Because it would have 2 different bonds on either side of it. Okay? Or another thing, we can say and or either one of these conditions would be sufficient. There's a lone pair on that central atom. That will mess up the symmetry of that molecule. So for example, in water, even though oxygen is bound to 2 identical hydrogen atoms here, it's got these lone pairs, and that leads to this asymmetry in the molecule where I can turn it in such a way that one end's negative and one end is positive. Okay? Cool. So then I want you guys to take a second, and for CH4 and NH3, we already said that water was what? Polar or nonpolar? Polar. Cool. So do these other 2 examples for me. I want you to label these as either being polar or nonpolar. All right, so CH4, polar or nonpolar? Nonpolar. All right. Which one of our two rules for polarity does this fail? So it's not asymmetric, it's perfectly symmetric. All those bonds are identical. It actually also fails the first one as well. Carbon and hydrogen bonds are not polar bonds. Remember, carbon and hydrogen have the same electronegativity, so those are never considered polar bonds. So this one fails all over the place. This is just a nonpolar molecule. And what about ammonia? Polar or nonpolar? This one's polar. Nitrogen and hydrogen do have different electronegativities, so we got some polar bonds in there. And what's the giveaway that this is an asymmetric structure? That lone pair on the central atom, right? Even though all of these are NH bonds, we got that lone pair on our central atom that's messing up that symmetry. Cool. All right, so our goal for today in our lab portion of the class is to go through a bunch of different examples and draw the perspective drawing of all of those different examples, as well as assign them as being polar and nonpolar and labeling bond angles, right? So again, we're going to kind of try to create a little master cheat sheet of all these different possibilities here. We'll get started on that a little bit early. We'll take our break and we'll meet here in 15 minutes.